Hello, and welcome to your Causal Inference 2 lecture. Hopefully this video is going to be relatively short. We're going to cover most of this material in class, but I wanted to give you a little bit of background, especially if you're not as familiar or haven't had a lot of the prerequisites that talk about linear regression and how coefficients work. I wanted to talk a little bit about how that works mathematically so that we can understand how that can help us do causal inference. Now, as a quick refresher, we talked a lot about some core DAG paths that we might come across in the various DAGs that we're looking at. And one of the main things that we talked about when it came to these paths is whether or not we want to condition on or control for various variables when estimating a causal effect. Okay, let's start on the right-hand side of this chart. For instance, when we have a collider relationship where both x and y cause z, if we're estimating the causal effect of x on y, we don't want to condition or control for z. Whereas the opposite is true if we have a fork on the left-hand side. In a fork, we have a kind of confounding variable, is usually how we refer to this, that causes both x and y. So if we want to know the causal effect of x on y, we do want to condition on or control for z in order to get the correct causal effect. For a chain, we kind of talked about we may sometimes want to control for, may sometimes don't want to control for. But essentially what I want to review here is that one of the things that we talked about with this DAG framework of causal effects is that there are oftentimes things that we want to control for or condition on in order to estimate the correct causal effect. Now, how do we do that? Well, that's what we're going to discuss in class. But one of the ways that we can do that is by adding variables as covariates to our regression. And in order to understand why that works, we have to take a step back and understand how regression coefficients work. So that's what we're going to talk about today. All right, so let's just remember what linear regression coefficients are. Here we have a bunch of code that doesn't really matter. We're just simulating some data, and then we're plugging this data into a linear regression. Here, we're looking at exam scores predicted by kind of the amount of extracurriculars that you have and whether or not you are accepted into college. Now, when we have a linear regression, we can print out the results, and in R, we know that kind of in this estimate column, we're getting the actual estimate of that coefficient. And so what we're seeing here, for instance, is that acceptance has a positive coefficient. If you are accepted into college, we predict that your exam scores are higher. However, we also see this negative coefficient when it comes to extracurriculars. That basically is telling us, or at least this regression, if we take it at face value, is telling us if you have more extracurriculars, you are going to have lower predicted exam scores. Now, that doesn't really make sense, and maybe there's something weird causally going on here. In fact, I can guarantee it is because I designed this problem. What I want you to focus on for this slide is what these regression coefficients mean. When we're looking at these coefficients, one of the things we've talked about is it tells you the relationship between your predictor increasing and what will happen to the predicted value. But the other thing that we need to talk about is when we have multiple predictors, what does that really tell us? Well, in a simple linear regression, one of the things you've probably seen or proved at some point is that when we do kind of a least squares or a maximum likelihood estimate for the different coefficients that maximize our likelihood or minimize our least squares, we essentially get something that looks like this. The coefficient in our regression is some correlation between our predictor x and our outcome y divided by the ratio of their variances. But this is when we only have a single predictor and an intercept. What happens when we have multiple predictors? So here we have some simulated data, and the reason we're using simulated data is because we now know what the true relationships are between our predicted variables and our outcome. So here we've simulated a bunch of data, and we can very clearly see two things. First of all, we can see what the actual regression equation is. We know that our y outcome data is x1 times 2 plus 0.4 times x2 minus 2. So our intercept is -2, and then we know what our coefficients are. They're 2 and 0.4. The other thing that we can see here is that x1 and x2 are correlated. In fact, when we generate x2, we are doing so centered around 0 plus 0.5 times x1, which means x1 and x2 are correlated, or in more specific terms, x1 is causing x2. All right, so we have our data, we've thrown it in a data frame, and we look at this linear regression. And we can see that we get these various coefficients, which are not horrible approximations of what we know the true relationship is. But how did we arrive at those coefficients? Well, remember, we just said on the previous slide that the regression coefficient should be the correlation between the two variables divided by the ratio of their variances or their standard deviations. So let's go ahead and do that. We can actually just grab that from our data frame. We can look at the correlation of x1 and y times the ratio of their standard deviations, and we can do the same thing for x2 and y. But notice, we get very different numbers than what we actually got from the results of our regression. Namely, one of the things I'm noticing is that the regression coefficient we kind of naively hand calculated for x2 is huge compared to the coefficient we actually got. And we already know, since we generated this data, that this is much more accurate. So if this isn't what's happening, what is happening? To understand what's actually happening, we have to take a step back and understand correlation. Now, correlation is basically talking about the shared information between two variables. So for instance, if we have a predictor variable x1 and an outcome variable y, the variance in y accounted for by x1, in other words, the information or variance that they share, is their correlation. Essentially, we're asking, how much of the information in y can be explained by x1? The correlation tells you exactly that. If we had a correlation of 100% or 1, basically we would say that all of the information in y could be accounted for by x1. The lower the correlation, basically the less information they share. But that's a regular correlation. We also have to consider something called a semi-partial correlation. The semi-partial correlation is a correlation just like a regular correlation, but now we've involved a third variable. The semi-partial correlation is the correlation between a variable and another variable after subtracting the influence of a third variable. So in this case, we basically have two predictor variables, x1 and x2, and an outcome variable, y. Now, x1 and y share a lot of information. We already saw that with the correlation. But what the semi-partial correlation is saying is, let's also bring x2 into the mix. Now, when we bring in x2, there's some information overlap that is explained in y by both x1 and x2. It's this weird little kind of like beauty blender shaped area right here. So when we look at a semi-partial correlation, we're actually looking for the variance in y accounted for x1 after we already account for the variance in x2. So when we look at y, we're basically subtracting out all of the variance we can explain with x2, which is kind of like this area right here. And then we're looking at how much of the variance in y can x1 account for after that or apart from that. And so you can see it won't be the entire correlation between x1 and y because some of that's also accounted for by x2. Rather, it'll just be this area here, kind of this weird little shape right here, that is independently in x1 accounting for information in y. So again, to review, a correlation between two variables only considers those two variables. It basically looks at the information shared between those variables, or in other words, how much of the variance in our outcome can be explained by one of our predictors. A semi-partial correlation, on the other hand, includes at least one other variable. We're basically asking the question, once we've already accounted for the information we can find out from x2, then what does x1 add on top of that? Now, if we go back to our kind of naive approach of estimating the coefficients versus what the coefficients actually are, this might start to make sense. Remember, x2 is caused by x1. There's a lot of information in x2 that comes from x1. That makes sense because if we look at all of the information in y that x2 can explain, a lot of that probably comes from x1, because remember, x1 is causing x2, and then x2 is causing y. So some of that relationship is due to x1's relationship with y. So of course, when we look at it naively, we're overestimating the impact that x2 has on y. Once we already know what x1 is, there's less information left over that x2 is actually explaining. So what do we actually do? Well, instead of the correlation, we are going to use the semi-partial correlation to calculate our regression coefficients. In other words, instead of just looking at the relationship between each individual predictor and our outcome, we're going to look at the impact of that predictor after accounting for all of the other predictors in the model. So what does that look like in this simple case? Well, here's the naive approach. Here's what we actually get for our coefficients. And here is using the semi-partial correlations. The semi-partial correlation, if we actually want to calculate it, is essentially the correlation of the residuals resulting from regressing x1 on x2 with y. So we're basically saying predict x1 with x2. So like subtract out the information from x1 that x2 gives you, get the resulting residuals, and then look at the correlation between those residuals and y. So we're doing what we just said we were going to do. We're subtracting out the effect of the other variables, and then we're looking at what's remaining. What is the correlation between that and our outcome variable? And you can see that when we do that and then we calculate what the actual regression coefficient should be, we get something that is much more similar with some rounding error to what we actually get from our linear regression. Now you might be wondering what happens if we have not one extra variable in the model, but multiple. Well, here's an example where we have 3 different predictors. And as you can see, the results are pretty similar, right? So we get our actual estimates from the linear regression here. When we do the naive approach, we often have incorrect estimates. What do we actually do? Well, here we're calculating the correct way, our regression coefficient for x3. What do? We take x3 and we essentially subtract out the impact of x1 and x2. We do that by regressing x3 by x1 and x2 and then grabbing the residuals. So we're subtracting out the effect of all of the other variables. And then with those residuals, with whatever information is left over, we then correlate that with our outcome variable. So why did we talk about all of this? Well, remember, the important thing that we're thinking about when we're thinking about causal inference is how we can control for or condition on other variables. And one of the ways that we can do that is just by adding things as covariates into our models. It works because the way that coefficients in a regression are estimated are basically taking into account what is the impact of this variable after conditioning on or controlling for all of these other variables. Now, this is only one way that we can control for things, but it's definitely the one that required the most in-depth explanation. So I wanted to talk a little bit more about coefficients and how they work in this video. But that's all I have for you. I will see you next time.